So we have to be very clear, V is volts. That's a unit for potential. But EV is energy. That should go up here. This is a unit for energy. You can see it's a very small unit of energy. So we actually also worked out the conversion between these. 1 electron volt is 1.6 times 10 to the negative 19 joules. If you forgot that, you should be able to work that out just by plugging in. Since E is 1.6 times 10 to the negative 19 coulombs, EV is 1.6 times 10 to the negative 19 joules. You have your textbook with you?
No.
So you know that there's a bunch of important conversions on the inside front cover. So let's see if you can find electron volts in there. That's right, and is that the conversion? That's the conversion we were just talking about. So if you forgot what we just talked about, you can always look this up. So you actually get, this is going to be important. You're going to need to do this conversion a lot in the homework, converting between electron volts and joules. So anyway, here's the conversion. 1 EV is 1.6 times 10 to the negative 19 joules. But again, we shouldn't really need that inside front cover. We should be able to figure that out from this little logic we just went through. Okay. I think we talked about previously how it's important to realize that potential energy and potential are different things. We talked about how this was a very poor choice of names by the physicists because they chose names that sound like they're the same thing. But potential energy is in joules and potential is in volts. So these are different things. So it makes a big difference that EV is energy and not potential over here. All right, so the upshot here is even though the standard SI unit for energy is joules, you're going to have to work a lot with electron volts in this chapter because you're working with very small amounts of energy, which are more conveniently measured in electron volts.
Is there a way to go between frequency and energy?
Oh, yeah, that's the whole point. Yeah, all right. So, yeah, what is the way to go between those? Have you seen that equation that relates energy and frequency?
Maybe.
Look familiar? Not? No? Okay. You might have missed that in the last couple of lectures. Okay. This is actually going to be a crucial equation from now on. E is for energy, F is for frequency, and H here is Planck's constant. H is Planck's constant. Let's see if we can find Planck's constant on our covers here. It's either, it might be on the back cover.
No, it's to the negative 34.
Oh, there you go. That's right.
What is the one point?
I think it's on the back cover, which kind of is come off here. Here you go. So let's see if we can find, oh no, you were right in the first place. It's in the front cover. Good.
Play 6.63 joules per second.
Good, except I think you might have mispronounced that. I think it's joules times seconds, not joules per second, right? Okay, normally we're not actually going to plug the units into the formulas here. We'll just plug in the number. However, the important thing is notice if you're doing an equation with Planck's constant, yeah, so here we have this. So let's say we're using this equation. How should we plug in our energy? In joules or electron volts? Because otherwise it won't be consistent with this Planck's constant over here. So this is an important thing that you have to do on most of the problems here. Usually the information is given in electron volts, but before you can use this equation, if you're using this form of Planck's constant, you have to translate into joules. We looked up that conversion ratio. There actually is a different version of Planck's constant that's in electron volts, but actually I think it's a good exercise to do the translation, so we'll stick with this. I think that's what you're doing in this course. In the homework they didn't talk about the other version of H. Okay, so we'll stick with the version in joules. Well, let's say we have some red light. Do you remember what the wavelength is of red light?
Around 700?
Yeah, I think it's somewhere around 700 or 750. We'll say it's around 700. 700 watts?
Nanometers?
All right, so now we're thinking of the light as a wave, 700 nanometers. Let's figure out what the frequency of that light is. You have your calculator? Okay, that came out right. So you saw that you have to convert this into standard units of meters. Well, nano means 10 to the negative 9. So what we're basically doing here is you're erasing the nano and replacing it with 10 to the negative 9. Okay. And then you do the division, and you ended up with, say, let's just say 4.3. 4.3, what would be the units on that?
Meters per second.
Take your time.
Just hertz.
Yeah, hertz. I haven't actually plugged in the units, but I know since that we put in standard units, we should get out standard units, and the standard units for frequency are hertz. Cycles per second. Okay. Now let's figure out the energy. What did you get again?
2.8 times 10 to the 19.
Yeah, or I got 2.9, but we can stick with the 2.8. If you round off, you got 2.8.
4.
Okay, we just rounded off different. All right, so we'll say 2.8. What are the units on that?
Joules.
Yeah, so you plugged in 6.63 times 10 to the negative 34 for H, and we plugged in this for frequency, and you got your energy. Good.
So what's an electron volts?
Pardon?
What is it?
Well, what is electron volts a measure of? What concept do we measure?
Of energy.
Yeah, so if we wanted to, we could translate this into electron volts. In fact, that would be a good next step. So let's figure out how many electron volts this would be. You might want to take your time and do that on paper as a formal unit conversion.
So 1 electron volt is 1.66.
Remember, it's based on that charge on the electron.
So
Good. No, that's not quite the conversion. Remember what's, yeah. E is 1.6 times 10 to the negative 19 coulombs, but EV is 1.6 times 10 to the negative 19 joules. How can we use that to do a formal unit conversion? Just take your time and do unit conversion the way you normally would if you were doing it on paper, step by step.
So if I have this number, kinetic divide by joules units, I get electron volts.
Okay, that sounds right. But actually, it looks like maybe you're not quite sure what the systematic way is to do a unit conversion. So why don't we review how do you do a unit conversion? So isn't this the way to do it? So the official way to do a unit conversion is you start by writing down the starting units. And then off to the side, you write down the target units. What are our target units here?
Electron volts.
Right. And then we have to put in a conversion ratio that will get rid of the bad old units and give us the good new units. Well, then what units do I want to put on the bottom here?
Bad units.
Which are,
Joules.
and then what units would I put on the top?
Electron volts.
All right, and now what numbers do I put on the top and the bottom?
So 1 electron volt is 1.6 times 10 to the negative 19.
Okay, that's where this conversion, that's where this equation comes in. The equation just tells you the numbers, what to put on the top and the bottom of your fraction. But how do you figure out who is the top and who's the bottom? Well, just by asking how can you go from your target units to, from your starting units to your target units. So here the joules would cancel. So the big mistake people make here is they don't know whether to divide by 1.6 times 10 to the negative 19 or multiply. But if you actually write it out formula like this, we should always be able to figure it out. So the whole point of an inequality like this is just to give you things to put on the top and the bottom of the conversion ratio. And then we have to decide who goes on top and who goes on bottom.
And then 1.8.
Yeah, I got 1.75, but we're rounding off. Okay, so we'll call that 1.8. What are the units on that?